Yes, welcome to this tutorial, just basic introduction to what we call vibration analysis in SolidWorks. I will explain what it's all about, and we want to introduce key terms that are used in vibration analysis, or what is the another name for vibration analysis in SolidWorks. So we will also understand what are natural frequencies, resonance, and mode shapes. So our objective is to understand basic terms used in frequency and analysis in SolidWorks, and how can we do a basic simulation or basic frequency analysis in SolidWorks. So in this case, when you hear the word vibration, it means oscillation. So this is simple, the study of you are looking at, or you are examining the oscillation motion of a structure or a component when you subject it to forces like structures. When you're building high-end buildings, you may find those buildings may be at the joints they are putting structures to prevent vibrations, or dampers, or the foundation they are putting dampers, or at the top of the roof they are putting gyroscope. So in these scenarios, they help to balance the natural frequency so that the structure doesn't fail. In mechanical systems, here I want to demonstrate on mechanical systems when you are subjecting a component to a structure to a vibration, the system may fail, or it may affect the around. So how do we ensure that we cover the effect of vibration analysis or frequency analysis? So in this case, we have the engineers always determine the of the parts or assemblies that responds to the dynamic. So vibration analysis is also called frequency analysis or frequency vibration analysis. In this case, engineers use these frequencies to predict the failure due to the. It also helps engineers to improve the stiffness and strength of their parts or component or machines when they are designing these structures, and also ensure to call the factor of safety to ensure that the performance of this system can all points before it reaches the bathtub curve failure or its expiring point. So in this case, when you see this body, this is an animation moving back and forth. This is what oscillation. It is oscillating. So how will you prevent? So yes, more structures or components in real scenario, they are not rigid. They always vibrate at various points. So if they are vibrating, how do you beyond the resonance level? What I want to discuss is what we call natural frequency. Natural frequency is the frequency at which a structure tends to vibrate when it is disturbed without any external forces. So that's when we say a system is undergoing natural frequency. If there's no forces which are being subjected to this system, in SolidWorks we will do what we call frequency analysis. We always calculate several natural of the part or assembly. An example, we will be using a cantilever beam, but I'm going to use a hacksaw as a cantilever beam. We see how this hacksaw will vibrate when you are getting to various forces. This is where you to calculate what you call natural frequency. Fn is what you call natural frequency, is measured in Hertz, and then K is always the stress measured in ton per meter in kilograms. So this is the formula: 1 times the square K over M. This is the formula we use to calculate natural frequency. So we also see in SolidWorks how can we achieve this system. How do we know that the system has is behaving naturally, and how do we know it is behaving due to what we call resonance? So resonance occurs when now the frequency of the external forces matches the system natural frequency. We say now the system is under resonance. The danger of this is that when you increase the frequency or the amplitude of vibrations beyond the natural frequency, this system will always be damaged, or the structural system will fail. That's when we say a system has failed, because you have exceeded the resonance frequency of the structure. For it to balance, when the system is at equilibrium, it means the natural frequency and the forces subjected to the system have balanced. So if the balance at a certain point, it means they have what we call resonance. But in case you increase the vibration, or the system vibrates more than the natural frequency, then that point is when we call the system has failed, because due to what due to vibration. In SolidWorks, we use this system to ensure that it operates within the frequencies that do not overlap the natural frequency. If it overlaps the natural frequency, automatically the system will fail, and that's condition when we say it is resonance. We can see this F excitation. It means the forces has been increased, or the vibration has been increased beyond the natural frequency. If it is or approximately equal, then we say the system is at equilibrium. But if you exceed the forces excited, or the forces being applied, or the vibration being applied on the system, then at a point the system may fail, because you have exceeded what you call the natural frequency. So at resonance, vibration amplitude is always maximized. This is the formula we can use to calculate what we call the amplitude or deflection of the system. So another term we can also learn is called mode shapes. So mode shapes is the deformation pattern of a structure and how it assumes the natural frequency. Its natural frequency, there are various mode shapes. So when it is deforming, it gives you a certain pattern for that structure. So in SolidWorks, we display mode shapes using a symbol forces. It's like here it is bending, it is undergoing to the rotational force, or it may be twisting. So the importance of mode shapes is always it helps to visualize the structure with to visualize how vibration will affect the structure. It gives you, let me say, a visual representation of how the system will behave when you add other forces. And sometimes it helps us to know where can we add stiffness, or where can we add dampers, how can we improve this system so that we get the required equilibrium. In mathematics, we normally calculate what we call eigenvectors. Those people who do what we call vectors. When you're using vectors, eigenvectors and eigenvalues, this one will help you to attain what we call the mode shapes. This M is this M, you have M and you have X dot, which means under velocity. This is K stiffness, and then X is the displacement. So velocity, and here you have these are acceleration, then these are velocity, then you have this zero. Solving the problem, it will always gives you the value omega as natural frequency, and the eigenvalue X as the mode shapes. So this omega will give you a natural frequency, and then this X will give you the mode shapes or the eigenvectors. So this one I'm not going to do mathematical, but I'm going to demonstrate how can we visualize on mode shapes from the equation. And then we have what called fundamental frequency. This is the low frequency of a structure. You normally call it the first mode shape. When you obtain the first mode shape, now this is what we call fundamental frequency. I will show you this frequency is all about, or what this fundamental frequency is all about. This is, you can say, at various points, maybe critically, it always responds to the frequency when it gives you the first mode shape. So in SolidWorks, frequencies studies always displays the fundamental frequency using the first mode shape. As I've demonstrated, if you have a first mode shape, this will show you what we call the fundamental frequency, the lowest natural frequency of a structure. This is the formula to calculate what we call the natural, the first mode shape using omega 1 over 2 pi, and then you are calculating now the mode shape. You can use the formula for fundamental which is equal to 1.875 squared over 2 pi L squared times 2 times this is EI density area. These terms I want to explain now. I will demonstrate physically using the software, so that we're able to understand these terms in the software. And then we have another term called dynamic loads. So these are the loads that that may vary at various points when you subject to a structure, and are the one that causes the structure to vibrate. We call them dynamic loads because they are varying with time. We say dynamic, they are changing. That's why we say varying with time, it means they are changing. That's why we call them dynamic loads. They may be changing. An example is like if a machine is rotating, always there is effect of wind. For example, an example of machine rotating, maybe wind loads, seismic loads, that is, we call them earthquakes. We have what we call impact or balance forces. This one are the one that comes about to create what we call dynamic loads because they change with time. And when you are using SolidWorks and analyzing this, you can either use what we call time history, harmonic, or random vibration. So we'll see simple. Can we do a simple random vibration in SolidWorks, and then we study how it will behave. There are various types of vibration analysis in SolidWorks we can use. First is frequency analysis. So today I will demonstrate on what we call frequency analysis. This one are the one that helps us to calculate what we call natural frequency in the mode, because we want to learn what are these natural frequency and what are these mode shapes. So we want to understand how can we use this frequency analysis to study natural frequencies and mode shapes. Also, we have another type of vibration called harmonic analysis. The studies upon what we call sinusoidal loads at different frequencies, like a sine wave or a sine curve, or let's say a sine curve or sine wave. So we can use these harmonic motions to study vibration analysis in SolidWorks. We can also do what we call random vibrations. This one normally simulates the loads with unpredictable nature. For example, rod vibrations. This one you can use what we call random vibrations. What we call transient analysis. This studies response to time with varying rods like shocks or impacts. Something you subject it at various points abruptly. We can use what we call transient analysis. So SolidWorks uses what we call finite element method or finite element analysis to solve the eigenvalue problem numerically. At the same time, it also provides you what we call natural frequencies, mode shapes, and how the system responds to frequency under different dynamic modes. There are various steps we are going to use. Maybe these are the key steps I'm going to demonstrate. To use, and then we want to see how can we attain these frequencies in SolidWorks. The first process is to prepare our 3D model file or 3D model of a hacksaw. I already have done that one. Then second is to assign the material. So I'm going to assign the material that has all these properties like the Young's modulus, the density, and the Poisson's ratio. Then from there we will define our fixtures. So I'll also show you where we define our fixtures. Defining our fixtures it means that we are fixing a place, or let's say the handle, where we grip the, let's say the hacksaw, to constrain certain movements, so that we allow only movement in various points. Then we can also define our connections. If we have contact points for the blade and the frame, I cannot do that. Then we also create a mesh. We can create what we call set parameters. We can set our parameters. We can also calculate what we call the so after running, we can calculate this, and then we can integrate information. From there, we validate, and then we optimize. So these are the key procedures you can use when you're doing frequency analysis in SolidWorks. So let's go direct and understand what and what I've covered today is what is this natural frequency and how does it affect the structure. What are these resonance and how does it occur? When the excited frequency or excitation frequency goes natural frequency, then it has reached what we call resonance. But beyond resonance, it now excited frequency is more than natural frequency, the system will fail. Then you have what we call mode shapes. These are the deformation patterns at the various natural frequencies. Then you have what we call the fundamental frequency. This is the first lowest natural frequency, which is very critical. Then you have what we call dynamic loads. These are the loads that you subject to a system to cause it to vibrate at various loads. Then in summary is that analysis in SolidWorks helps engineers to design a safer, more reliable mechanical systems that helps engineers to predict how the structures will respond to dynamic forces and how will avoid dangerous resonance conditions. So let's go to SolidWorks and then we do a step this guide. How can we do animation analysis, what we call frequency analysis in SolidWorks or hacks? That's our main objective. So this is what you are going to cover. Ensure that you have activated your system. So you go to what you call the add-ins. Then you, under the add-ins on the options, you can now activate what you call SolidWorks simulations. SolidWorks simulations. Once you have done that one, it will come to what we call feature manager design tree. So this is the hacksaw we are going to use to demonstrate our today's topic on what we call frequency analysis, to see natural frequencies and to see to visualize what we call the mode shapes. So let's go one by one. So the first procedure is click here. You click a new study. Once you have your simulation activated, because I'm doing frequency, as I said, we have what we call frequency analysis in SolidWorks. We have what we call linear dynamic analysis. We cannot do what we call linear dynamic analysis and other analysis in SolidWorks we can, but today we want to do what we call frequency analysis. So just right here, maybe for example, hacksaw frequency. Let's say hacksaw frequency analysis. That is the title of my frequency or my analysis. Then click OK. Once you do that one, it will always come here. This is the name for the name we have created. That is hacksaw. Under status bar, below the status bar, we have what we call hacksaw frequency analysis. Then here, the first procedure is to develop your model. That is the first step. Already, I have my 3D model for the hacksaw to represent the hacksaw. Then the second step is to create a study. Then the third step is to apply the material. So we apply the material. I want to apply a material for that has the Poisson ratio, that has the mass density, that has the shear modulus, and has the elastic modulus. So these are the features we are going to apply. I'm going to apply alloy steel for that one. Click apply. Then that is the third step. Apply, then close. Then the next step is apply our fixtures. So we come here to apply our fixtures. So here, click on fix geometry, and then we can pick our geometry. Click on the first face for the handle, because that's where we are going to handle, and then this one to restrain our motions. Then click OK. And then next is you can pick the load, load or connections. Let's pick the load, the force. We can pick the force. Under my force, I want to use selected conditions. Then here I say top plane. From top plane, I can pick this edge. Let me pick the last one. Then I can pick this edge, and then I can reverse, so that I'm only using like a cantilever at the end of it. So this behaves like a cantilever, and let me use 1 Newton. I will modify my design one by one. So this using the top plane, selected direction top plane, and then I'm using like a cantilever. Then I click OK. And then here I can also add connections. The contact points, for example, the one we are looking at this. But for this case, I want to ignore this one first. Then we go to create a shell or create a mesh. In this mesh, I want to just use by default. Not make it so fine here, because it may take a lot of time to run. So let me use the default one. Okay. So I'm following the step on what we have covered on how can we do a step-by-step vibration frequency analysis or vibration analysis in SolidWorks. So it's doing the mesh, creating the mesh. When you say finite, it is small. So it must create a small particles or small shapes or small elements. Let me use small elements. It must create a small element. So that's what we call Finite Element Method. So you're using what we call FEM. So these are the mesh. So you see these patterns it has made. We call them the finite elements. These are the finite elements. So one, we have put our fixture. Second, we have constrained our model. Next, we have put our force at the far end of it. Then it behaves like a cantilever. Then third, we have created a mesh. The next is we now run the study. We click now run this study. It runs the study. Depending on the powerful of the how powerful your computer is, it will be very fast, because these simulations require a very powerful computer to be very fast. And then once it runs, you see what displays. When I was giving you explaining what are these mode shapes. So this is the results. How many mode shapes do we have? 1, 2, 3, 4, 5. So the first mode shape, which is the lowest one, we call it fundamental frequency. So this is the fundamental frequency. So this is the first mode shape where we get F1 equals to omega 1 over 2 pi. That is the first mode shape we get. So you can look at these parameters here given in. Let me change this one to be floating. Maybe you can see what is given for the first mode shape. I can say use floating. Let me change this one. Let me use to floating. Then I can okay. Then I click OK. You can see this one. I can put it somewhere here. This is the first mode shape 1. You see it is given you the first mode shape, and it also gives you where the failure point is. The failure point is, it has this, that is the deformation pattern. The first deformation pattern of the mode shape will help us to calculate what we call the natural fundamental frequency. So how do we get the fundamental frequency? So you take the first mode shape value, divide by the 2 pi, you get the natural frequency for the fundamental frequency. So this region, as you see, where it is this color, it is below the natural frequency, which means it below natural frequency, which means the system may not fail. But when you are moving further away, applying the same load, the system may fail at this point where you're seeing these colors become from yellow almost to red. If I go to next, for example, click here. If I click this one, it gives me a second mode shape. For example, I click this. You see, this is the second mode shape. That is the deformation pattern. If I click again, it gives me the third mode shape. If I click again, it gives me the fourth mode shape. If I click again, it gives me the fifth mode shape. Bending, twisting, torsional, all of them are balanced. Next is the first mode shape. You see the first mode shape, how it behaves. I can also do, let's say, animation. You can see how it behaves when I do a simple animation for the first mode shape. This is the first mode shape. This is the first mode shape. I can come to the second mode shape. This one, activate this, show this, and then the second mode shape, and then animate. We see how the system behaves. You see the second mode shape. So if you're using your hacksaw, and maybe the hacksaw was the blade is not stiff, it doesn't have the correct strength. When you're using it, at various points you see this behavior. Then we can check the next mode shape, the third mode shape. Let me show third mode shape, and then animate. You can see how it will be behaving, the deformation pattern. So it helps you to understand where you are going to improve the strength, how you are going to ensure that the material is stiff, so that it prevents this aspect of deformation. That is when you're using the hacksaw. Next mode shape, maybe I can show this one, and then I also do animation for the next mode shape. You see how it behaves. The fourth mode shape, this is the behavior. The fourth mode shape. We can go the last one, the mode shape. How many? There are 5. Show, then animate. So this is the fifth mode shape. It is twisting. You see, the blade will be behaving like this. So these mode shapes will help. We call them deformation patterns. It helps you to understand at various points how are you going to solve it, and how can you get the values for the mode shapes. I can come again to this first mode shape. Show first mode shape. You see here on this chart. Let me put somewhere here. You see this note. It is saying the model name is hacksaw. The study is hacksaw frequency analysis. Then the plot type is frequency amplitude. Then the mode shape 1, the value 1, which is given as this 78.8339. So if you take, for you to get now the what you call the fundamental frequency, because fundamental frequency is obtained from the first mode shape. So you take 78.839 divided by 2 pi. Divided by 2 pi. Let me do using my calculator. Sorry for that. 2 times pi. 2 pi divided by 2 pi. You will get 12.55. That is our fundamental frequency. So our fundamental frequency will be 12.55. If you are doing now analytical calculations. So you do analytical calculations and then you compare with the software. How will it vary? If they are close to each other, then it means the system is, you have done what you call design analysis. That is a design analysis under vibration analysis. Then we can also go the second mode shapes. Show the second mode shapes. You can see second mode shape is now 426.67. So you have to look at the what was the natural frequency of your blade. What was natural frequency required for this blade? Then you compare with the frequency you are getting. So when you be omega 2 over 2 pi, it gives you the frequencies at every various points for the mode shapes. So those are what you call the eigenvalues. So the eigenvalue for this is 426.67. So does it deform beyond the recommended? And then it also give you the scale. The scale. This is taking the average of this. If you go to the third one, we are able to see the third one. If we go to the fourth one, we can see the fourth mode shape and the last mode shape. We can also show the last mode shapes. You see the mode shapes, the frequencies are increasing as you go from mode shape 1 to the last mode shapes. So this one will help you to come back to your design, see how you are going to improve your design, see how you are going to optimize your design, and ensure that this won't fail when you design the model and when you manufacture or you produce the model, they say the hacksaw to be used in the industry. So this is what we call frequency analysis. And what we covered in our basic introduction, we covered what we call vibration analysis, and we say there are various types of vibration analysis. But the first one we have done is what we call frequency analysis, to visualize the various mode shapes, and also to visualize what we call fundamental frequency, and how the system fails, where we have what we call natural frequency and what we call the resonance, where you excite the system at various points when it vibrates, and if you get the value equal to natural frequency, then the system is at equilibrium. But when you exit the vibrations, the excited vibration or the applied vibration being more than the natural frequency, then the system goes what we call failure. It may fail at various points. So vibration analysis is good for engineers. It helps you to understand how you're going to improve the system so that you design a system which is more safe, reliable, and performs to what it's required to perform. At the same time, it is durable. So this is an introduction to what we call frequency analysis. In the next phase, we also look at what we call how can we also improve this system to ensure that we optimize our system to before it is being produced for industrial use. So welcome and enjoy today's topic for this frequency. You can also generate a report once you finish here. For SolidWorks, actually, it is very basic. You can create a report here. You can now just create a report, then you submit. Maybe here I can say design of hacksaw as my description, then frequency analysis of the hacksaw blade, sorry for that, blade. And then I can put the designer, let's say this is engineer Kim. I can put the company, I can say this is Dalkrins Technologies. If I want to say the report, Dalkrins Technologies here, the technologies, I can put maybe the website. I can say www.dalkrinstechnologies.com. I can put the logo. I can browse my logo here. Let's say logo here. I can put my logo. Let me put a simple logo. All files. I can put a logo for my downloads. W. Let me check the logo. This is a simple way of. I can put an address, maybe Enterprise Road. Industrial area. I'll call it Avon Center. Can put the phone. I can also put my email as Dalkrins technologies dot at gmail.com, and also my contact +254, because I want to send a report, 254 713 66902. I can put the phone number here, +254 702 for the company 801545, and I can say where I'm going to save it, and this I can display, and then I can say apply. After applying, say publish. Then the system will write you the report. You see, it writes the report very easy. It is writing a report. So this report I can send to somebody. Once I've done my design analysis, I can send the report maybe to the client. They're able to see where the failure point is, how I'm optimizing my design, and how it should be produced depending on the design analysis I have given them. So they also compare the analytical values with the design analysis values or software analysis values. So this is SolidWorks. That's how powerful SolidWorks is. How powerful SolidWorks is. It may not be so powerful, but it is good because we can also use Creo PTC, which is a basic software for design analysis. We can also use ANSYS, which is a basic software for analysis, that is finite element analysis. Let's finish the report. I know it is beyond the objective of what you're supposed to cover, but this is for the purpose of, in case you want to send the report, this is how you do it. It's also almost, sorry for taking time. It's almost, yes. Now it opens the report, you see. It opens the report for you. You see what I had put? All of this. The SolidWorks has done everything for you. So the model, when you come here, giving you a table of content, you can also come here, also type whatever you want. Assumptions, if there are assumptions you can put, because I've not put assumptions. This is the model. You can see the mass of it, the volume, density, the weight, and even where it was saved, you see, and what time it was done. So if there's a student doing analysis, they cannot lie. You see, it can give you everything unless they edit. But once they edit, you're able to know, because they send you the soft file, and you can check the location. You see, these are the study properties we had put, the units we are using. This is the mass properties of this materials: alloy steel, linear. We are using what we call linear elastics, isotropic analysis. The failure systems, what we call von Mises stress analysis, and we're using a solid body to do an analysis. Then here we had put two phases for the purpose of loading our fixtures or defining our fixtures. Then it is also giving the load conditions. So you're putting 1 Newton, for example. In case I wanted to use more than 1 Newton, you can put the values. And then the connection pattern, they say I'm jumping this one, but when you put in the SolidWorks, it also give you the connector pattern. For example, where you are clamping, you are loading, you are connecting to the blade, the handle. Here it is putting the mesh conditions, how many points you are using. We are using what we call Jacobian points for the high quality mesh. And then the measure type is what we call a blended curvature based mesh. Then here you can also see the total mesh values or elements. That's what we call them finite elements. These are the total elements, 11,473 elements. How long did it take to do calculation, to compute? It took 30 seconds. How fast is this? They also give you elements for the value for mode 1. That is the mode shape 2. It gives you the mode shape 3. It gives you mode 4. All the mode shape values gives you and how it behaves, and it gives you a summary of the frequency number 1, the value for it, the has, and the time it took. So this is the omega 1, this is omega 2, omega 3, omega 4, omega 5. And this is the what you call the eigenvalues. Eigenvalues. You can calculate eigenvalues. You have all of them frequencies given one by one. All of them are here. You can see for different mode shapes. Mode shape 1, 2, 3, 4, 5. The value for X value direction, Y value direction, and Z value direction, and the sum of it. So it does the sum down there. Then conclusion now, if you feel the design is okay, it's you now who is a designer and analytic guy to give the conclusion in your design. So this is how you can do your design analysis in SolidWorks using what you call frequency analysis.